it's always interesting to see how things are implemented on different platforms. So our next two speakers did exactly that, a port and platform. So please give a big round of applause to Felix and Alexander Couzens.
It started basically that Felix came to Berlin and had a new board in mind he'd like to have, or I think he already had it. He sent a package to me and came a day later, and yeah, we worked on a HD microserver, which is a really nice board. It's a really cheap one, so you can get it with multiple CPUs. The lowest one is just you get the whole system for 200 euros, even with trays in it, and also with ECC memory, and even a management controller, which was new in difference to the version before. And yeah, coreboot sounds really interesting because this is a Sandy and Ivy Bridge system, because the CPU is Ivy Bridge, but the chipset is Sandy Bridge. Yeah, so if you're going to create a new port, you really to look into everything, what you have there, what's in there, how the system really works. So there are the simple things like LS USB, LS PCI. You can try to use autoport if it's Sandy Bridge, or I don't know how many platforms we support by now with autoport. But you should also look at the chips, what we have there. And so basically this is the board. If you pull it out of this is small. I don't know, we don't have a picture of the whole device, but it's really nice. You can really simple disassemble it and pull out the whole board, and yeah, you see it's the memory, of course. There's the CPU, but the interesting part is there's this IPMI, the management controller. We have also here's another chip that's an FPGA. We have, strangely, here we have an eMMC. I don't know for what it is, but yeah, so here's probably the chipset, and we have a lot of connectors, also here interesting connectors maybe, also here, and we have some network cards on it, so a lot of different things. But yeah, how do server boards actually work, or at least this server? And strangely, somebody, if you search for it on Google, you find this really nice picture, which was released on a blog, somewhere written here, and they got it before the complete board was released, and it's really close to the board. So you see basically, you see here that this is the management controller, and yeah, so. And it's really true that we have also here the CPLD, we have some non-volatile memory, some really strange things here, which isn't still kind of why and how. So we are not totally finished yet, but we had a lot of fun already. Yeah, so then we started working on it. We just to look at the chips there.
On this graphics, which is different to most boards that are ported, is that you don't only have the processor with memory and chipset, but also have this system management and this integrated lights out controller, I think it's called. And yeah, that makes the system different. But to be able to develop on that board, we want to access the flash chips. But on some flash chips, you can't just connect a clip because the other components on the board would interfere with that. And one possible solution, when you have enough space on the board, is to solder a real socket on that and then put the chip into that socket. But those sockets are not that cheap, and you need quite a big area for that. So we took hot air gun, desoldered the flash chip. That's the firmware flash for the integrated lights out management thing. Then we soldered some wires to that. And when you buy those SOIC8 clips from China, you get also this small board with it. And so we soldered the chip, we desoldered there on one of those small boards, and soldered the wires on the one end on the footprint, and on the other end on two 4-pin connectors. And so we can plug that small board with flash chip into those connectors. And the flash chip just pull it out and put it in the flasher and update it. So it's a cheap solution and quite easy to use.
Yeah, and this is one board what we have here now somewhere. I don't know where that lies around. We have this board with us, but at my home we have even improved that solution, that we have a small PCB that we can remotely flash BIOS without having a full flash emulator. So we can remotely flash and test also new coreboot versions. So when we first started, we just basically rebooted once. Does the system really work? So we can still give it back, but afterwards we desoldered all chips and looked in it. And yeah, it has quite a lot. So Felix thought about this big one. We have also the BIOS chip, which is also quite interesting because it's separated from the IFD and ME. Yes, this is the Broadcom firmware, and it also contains the PXE stuff. Then you get with the server, you get the small tag where the default password is and the serial number and all this stuff. Yeah, so, and this is still, the question, why the hell is there an eMMC? I think with 256 megabytes, I don't know, a lot of space, no idea for what it is used. Yeah. So,
then we had a look at the board and the connectors that were not soldered. There was this, this 38-pin connector, which looks quite familiar to the ARM trace connector. And I had a look at the documentation of the pinout, and it seemed that it matched. And then I soldered some wires to that and connected it to the JTAG adapter. And the other, it's a bit about the jumper, the four soldering pins in 2mm pitch. That turned out to be the UXC report of the ILO. Yeah, well, you used a multimeter to find the ground pin, and then just connected some cables and connected logic analyzer to that, and looked what looked like serial communication. And the line that looked like that, we connected USB UART chip. And that's what we got out of the integrated lights out chip.
I think the interesting parts are up there. If you, I don't know if you can read it, but it says starting decrypt, which is really interesting, and also how, also where to decrypting it. But,
and also decompressing afterwards.
Yeah. Right.
So we connected the JTAG to the connector I showed before. Started OpenOCD and let it search for the devices on the phone. It showed quite a lot of devices, so there's something still probably wrong. But only this JTAG ID and this JTAG ID alternating. The second one is the lattice semiconductor FPGA. I think they call it CPLD, but in fact it's an FPGA with a non-volatile memory in it. And the other one has to be the IO4 chip. We still don't know really exactly what's in the chip, but probably it's a multi-die package because the chip is quite huge. It's quite huge.
And up there, there's a CPLD with a sticker on it.
Yeah, that's a programmable logic device. Then we used binwalk -e on that. That shows a graph of the entropy of the image over the image location. So yeah, that looks pretty much like compressed data or instructions. That looks like probably encrypted or good. Yeah, it has. And also some. There are two other compressed sections, and there is a section with not that much entropy, and it's 64 kilobytes big. So yeah, we took the image, sliced it into different pieces, and loaded it in IDA Pro. Well, it's 16 megabyte flash image, and turned out at the end there's the last 64 kilobytes is the flash bootloader, and the other part consists of the different sections. And the process architecture is slightly in ARM9, which has its reset vector either at 0 or F and 4 zeros. So yeah, loaded that the last 64 kilobytes into IDA Pro. It showed the vector table with entry point and the different handlers. And there were also 3 other values, which are in the area or slightly after the second reset vector. And at those locations, there is actually code that makes sense, and is also jumped from different parts, so we can be quite sure that this is the reset vector which is used for the flash bootloader. Then we had a bit more of a look at the flash bootloader. At the entry point, it goes into a rather long function where IDA Pro had some problems decoding it, because they call some function, and there are strings after this function, and inside that function it loops over those values and calls another function with each byte. And yeah, that string, we've seen that in the serial output. So we can be quite sure that the function that is called for every byte, it's put-C. So we have a look there, and in the 0xC and 7 zeros, in that memory area, there were some registers, which turned out to be the UART data register and status register. Yeah, and the printing routine, after it reaches the 0 byte at the end of the string, then it calculates the return address, or the
I think return address or the program counter, so the print function knows where.
So that the code flow continues right after the string and the padding, because it has to be 4-byte aligned. And yeah, there were quite a lot of those constructs in the beginning of the flash bootloader. Well, then of course we had to try if you can get a code execution on the integrated slides out management chip. So I took the flash bootloader and replaced the first string with hello ECC'17 and added an infinite loop after that. Flashed that to the flash, connected the flash, and saw the hello ECC'17 on the serial output. So now we know for sure that there's no code signing involved, and so it would be possible to port the OpenBMC to that. At least possibly it's probably quite a lot of work, but yeah, it can be done.
Yeah, now we're looking at the BIOS image, and if you look closely, you can maybe mirror it at here. So it's nearly the same. You see it looks nearly the same. So it's actually you have 2 by 4 megabyte images in there, and yeah, that's how it works. It's also telling it that it has a backup. If you look at the VM bootloader,
even the web front end from the ILO shows there are 2 images.
So somehow the ILO is interfacing it, but it's not a little bit more interfacing it because this system doesn't boot from SPI, it boots from LPC, and it boots from LPC through the ILO actually. So the ILO reads out the flash and maps it into the LPC, and the system boots in from the LPC. We haven't yet figured out how they communicate. So yes, there are LPCs and there are also LPC logical device nodes. But somehow when we replace the chip, the flash chips, and put them on those small PCBs, I also took other PCB which I already prepared with a different type of flash chip. And so OEM BIOS detected it. That's not the same flash chip which I expected, and tells you to please fix that and come back later. It really stops booting. Yeah, then we tried to do autoport. It went not so well because somehow the SPD bombs of the RAMs are not there. We found also some traces within the ILO serial output which say yes, there's some SPD feeder, so I guess it's also somehow proxied over the ILO. We haven't found out yet how it works, but we just read out with the different boards, the SPDs, and tried to place them. We do the same like on laptops where the memory is soldered onto it. They also don't have an SPD, but that also didn't work out quite well because yeah, when it tries to do the cache as run migration, that's the step when it switches from running directly from the LPC or from the SPI flash to the RAM stage. There it stops working, and yeah, we haven't figured out what's the exact problem. But we have also by now we have serial output, and we not only have serial output, we have it also over the ILO. So we can completely say we use the IPMI tool over network, say hey, please shut down the system, and we flash it. Then we power up the system with the IPMI, and also access the serial output over the IPMI. So that works well so far. So we could try it, so we can speed up in developing. We don't have to flash it anymore manually. Yeah, so that might be one of the next steps where I'm working on. I've done a little bit of progress on an LPC sniffer based on FPGA. So far I can decode addresses, and now I need also to the data, decode the data. And yeah, so basically this is where we are right now, that it hangs at the car migration.
Yeah, so thank you for your attention, and any questions?
Well, I fixed the microphone problem in the last second. So it seems like your microphone went a little bit low in volume.
eMMC on the board. Do you have any idea how it's connected to the CPU? As far as I know, the IB bridge hadn't any AMC controller inside. So just USB attached, or is there a PCI Express attached?
No, we have it on a slide, actually, or we found it on the internet. And we found also in the serial UART there was something about file systems, so I could imagine maybe the ILO is accessing it. So we have here, it's called just NAND, but I guess it's connected here, but I don't know how
it's actually USB attached storage.
The micro SD card and the NAND flash are attached via USB. And that chip also has an SPI slide-back interface to the ILO chip. Okay. And the ILO chip is connected via PCI Express, mostly for graphics, and also I think when you refresh from the host, it also accesses the PCI Express interface. And the LPC interface for booting and Super I/O functionality, and also a USB interface. I think it's used for keyboard and mouse emulation, or something like LPC.
Yeah, right. I think also over USB, but actually on this thing is also missing a connection because the ILO is also communicating over an I2C interface to the ME. That's, I think, not that there, right?
Yeah, we haven't completely verified that.
Yeah.
Okay, thanks. So I don't know how much you've worked with these ILO type things, but generally they have the ability to forward the VGA display via a web page. All these companies like HP love this stuff, and so you have like a web UI that acts like the keyboard for your mouse. And so that NAND 4G, doesn't that sound like 256 megabyte of NAND flash for the ILO? I don't know, because frequently these ILO operating systems are gigantic. For, you know, these ARMs run, it's just amazing.
I think the decompressed and decrypted image is maybe 23 megabytes.
Oh, okay.
And it's probably in the flash, and the NAND chip maybe contains some drivers for easier driver installation for the operating system. I haven't verified that.
Yeah, I think maybe we saw one case where they had Windows drivers in there. But there's a funny story from an early port that Stefan did on the new ISIS. It had an ARM ILO type thing running hardhat Linux, and it took 5 minutes to boot the thing that let you turn it on. So when we put Linux BIOS on it, we boot Linux on the Optron in 3 seconds, and 4 minutes and 57 seconds later, the ILO was ready to be talked to. So anyway.
So, any more questions? No more questions. Okay, then let's give it a round of applause for these two guys. So in about 20 minutes, lunch hour will start. So yeah, we see.